Hi, in this lecture we will be looking at the concept of vector projection, and specifically we will be looking at projection of one vector onto another vector. Okay, so we will be given two vectors, vector A and vector B, and we want to find what is the projection or image vector A has on vector B. Okay, so how will it look like? So let us say this is our vector A. Okay, and let us say this is vector B. Okay, then the projection of vector A on vector B will be what? So if you throw some light on vector B, okay, so let's say this is our coordinate axis, this is x, this is y. You are throwing some light on vector B, which means the light should be perpendicular to vector B, something like this. Let's say this is our light source. Okay, so we are throwing light on vector B. Then what is the image vector A makes on vector B? So the image will look something like this. So let us say this is the component. So this component is perpendicular. Okay, this will be perpendicular. So this will be the image. This will be the image which vector A makes on vector B. Okay, so this is the projection, and this projection will be like, it is vector A only, but it is the component of vector A which is parallel to vector B. We can write it like this. It is the component of vector A which is parallel to vector B. And similarly this particular vector, okay, this vector is what? It is the component of vector A which is perpendicular to vector B. It is not an image. So this is image, this is image. The projection is this image. But this particular vector is the component of vector A which is perpendicular to vector B. Okay. So this particular green component will be called, the projection of vector A on vector B. And you can denote it like this, or you can call it like this as well, projection of vector A on vector B. Okay. And similarly this particular component which is perpendicular to vector B, and it is the component of vector A only, right? So this particular thing, this perpendicular is called the rejection. It is called the rejection of vector A on vector B, and it is sometimes also called the orthogonal projection. It is sometimes also called the orthogonal projection because it is orthogonal to the projection, right? Orthogonal means perpendicular. So it is also called orthogonal projection of vector A on vector B, and it can be denoted like OProj, which means orthogonal projection of vector A on vector B. Okay. So this is what we want to find, this particular vector or this particular vector. How do we find it? This is what we will see in this lecture. Okay. So let's start. So the vector projection of a vector A on a non-zero vector B. Okay. Vector B must be non-zero. Then only you can find it. You cannot find projection of a vector on a zero vector, because zero vector is a point, it does not have a direction. We want to find the component of vector A in the direction of vector B, but zero vector does not have any direction, so you cannot find it on a zero vector. If you are finding the projection of a vector A on a vector B must be non-zero. Okay, so the projection of vector A on a non-zero vector B is the orthogonal projection of A onto a straight line parallel to B. Okay, so if you draw a straight line parallel to vector B, what is the orthogonal projection of A? What is the image which vector A makes on vector B? This is the projection. Okay, so in this diagram, again we have drawn it like this. So this is the vector B. Let's say this is the vector B and this is the vector A. Then the image which vector A makes on vector B is this vector. It will end here only. So the direction will be the same as of direction of vector B. The direction will be same, but the magnitude might be different. The magnitude will be only this much. So if theta is the angle which vector A and vector B make, then this is the diagram. This is how it looks like. So A1, this particular vector A1 is the projection. Again, you can denote it like this. You can call it vector A parallel to vector B, and this particular vector is nothing but vector A perpendicular to vector B. And you can also call it projection of vector A on vector B, and you can call this one as orthogonal projection of vector A on vector B. Okay, so we want to find this projection vector. Okay, and the formula is Projection of vector A on vector B is A vector dot B vector upon magnitude of B vector square times B vector. Okay, this is a formula. But how do we derive this formula? Let's try to derive this formula. So the hypothesis is, the formula that we saw is projection of vector A on or onto, you can write onto also, onto vector B is the vector, this is a vector which I am creating, this is a vector, okay, is the vector A vector dot B vector upon absolute or the magnitude of B vector square times B vector. This is the formula. Now let's try to interpret this formula first. Firstly, let's try to see what is it. Is this a vector also? So how do I see this? So if I try to break it down, A vector dot B vector upon the magnitude of B vector square B vector. So if you look at this particular part, this entire thing is a scalar. This entire thing is a scalar, right? This entire thing is a scalar. So we are essentially multiplying a scalar with vector B. Why is this a scalar? Because denominator is a scalar. Denominator is what? Magnitude square. Magnitude of any vector is a scalar, right? It's a value. So value square will be a value. It will be a number. Magnitude square. And dot product of any two vectors is also a number. Dot product is a scalar. And magnitude square is also a scalar. And hence scalar upon scalar, value upon value will be a value. It will be a value at the end. And essentially we are multiplying a scalar value to vector B. What does it mean? The direction will remain same. That's what we wanted. Whenever we want to compute the projection, the direction will remain same. If this is my vector B and this is my vector A, then the projection will look like this. It is the perpendicular. So this is the projection, right? This is the projection. This is a projection of vector A on vector B. This is a vector. So the direction will be same. The direction will be of vector B only. But the vector B will be multiplied with some, like we are scaling it. Either we are shrinking it down or we can expand it also. If vector B is smaller, we can expand it also. So essentially we are multiplying something to vector B. And that's what this formula is doing. We are exactly multiplying it by this much to get the projection. Now how? We want to prove that. So let's try to prove that. So here is the proof. Okay, so let's say the angle between vector A and vector B is theta. Let's say the angle between vector A and vector B is theta, and let's say the magnitude of vector A is this much, right? This is the magnitude of vector A. Then the magnitude of this projection, so this is basic trigonometry. This is basic trigonometry. If you have a line, and if you have to find, if this is a triangle, if this is a right angle triangle and this is the angle theta, let's say this line has a length of x, then this particular line will have a length of x cos theta, and this particular line will have a length of x sin theta, right? This is basic trigonometry, because we know that cos theta is what? Cos theta is base upon hypotenuse for a right angle triangle, and sin theta is perpendicular upon hypotenuse, and base is this much here. So the base here will be hypotenuse into cos theta. Hypotenuse is x, so this will be x into cos theta, and perpendicular, which is this, will be hypotenuse into sin theta, which is x into sin theta, right? So this particular value will be x cos theta if this is a right angle. And similarly here also we have a right angle. So the length, we now know because of basic trigonometry, we know that the length of the projection, it's very easy to find. The length of the projection of vector A on vector B must be the length of the vector A, which is the magnitude of vector A, times cos theta, if theta is the angle that is between vector A and vector B, right? So the length is sorted. And the direction also we know. See, now very important concept we are going to look at. We have seen that any vector can be represented as a combination of, let's say, something dot I cap plus something dot j cap. If a vector A has components in x and y direction which are 3 and 4, then I can call it 3 times I cap plus 4 times j cap, right? Now what does 3 times I cap mean? 3 times I cap is a vector of length 3 in the direction of I cap. I cap is a unit vector in direction of x-axis. Unit vector in x-axis. And this 4j cap is what? 4j cap is 4 times j cap. J cap is a unit vector in the direction of y-axis. Unit vector in y-axis. So essentially, what is a vector? Any vector is composed of two things, magnitude and direction. So if I look at the vector 4j cap, it is of length 4 in the direction of j cap. So whenever you are trying to create a vector, if you already know its magnitude, you can just multiply it with its direction. Direction is what? You can just multiply it with any unit vector in that direction. Think about it. So let us say, again, let's take the same vector, 3i cap plus 4j cap. Okay, so 3i cap plus 4j cap is this vector. It is 3 units in x-axis and 4 units in y-axis. So it is this vector. Okay. Now if I want to find a unit vector in the direction of this vector, if I want to find, let's say if I call this vector as a vector, then a unit vector in the direction of vector a will be a cap. Similarly, like a unit vector in the direction of x-axis is I cap. Similarly, a unit vector in the direction of a vector will be a cap. How do I find a unit vector in the direction of a cap, in the direction of a vector? I'll just divide a vector by its magnitude. If I divide this particular vector by the magnitude of a vector, I'll get what is the magnitude of a vector? The magnitude of a vector here is square root of 3 square plus 4 square, which is 9 plus 16, 25, 5. The magnitude is 5. So if I just divide this vector by 5, now I got a unit vector in the same direction. See, the direction is same. This particular vector is what? 1/5 of this vector. So 1/5 of this vector will be this much, whose x component will be 3 by 5 and y component will be 4 by 5. Right? This is a cap. And the magnitude of this vector you can check. The magnitude of this vector will be 1 and the direction will be same. Direction is definitely same, right? Because x and y component are same, like scaled down versions. So it is in the same direction, but the magnitude is 1. So this is a unit vector in this direction, right? It is a unit vector in the same direction as a vector. Now if I want to create any vector in the same direction, let's say if I want to create a vector which is of 5 length and in this direction, I can just call it 5 times this vector. This vector is what? 3 by 5 I cap plus 4 by 5 j cap, and I'll get the a vector again. If I want to create any other vector, let's say in the same direction I want to create a vector of length minus 5, or let's say I want to create a vector in the same direction of the length 10 units, then I can just do it this way: 10 times 3 by 5 I cap plus 4 by 5 j cap. Now this is a vector. This is what? This will be 6 I cap plus 8 j cap. So this particular vector is a vector of length 10 in the direction of a vector. This vector is a vector of length 10 units in the direction of a vector. So this is how you can do that. You just find a unit vector in the same direction and multiply it with the magnitude, and you will get another vector with that length in the same direction. So why did I tell you all this concept? I told you all this concept because here I have the length. I already have the length. This is the length. This is a scalar. It is a length. Now I want to find a vector. Vector has a magnitude and a direction. If I just multiply this particular magnitude with a direction, direction is what? It will be a unit vector in the direction of b vector, which is b cap. If I just calculate b cap, b cap is what? A unit vector in the direction of vector b. In the direction of vector b. So if I just multiply this length with a unit vector in the direction of b vector, I'll get the projection. So the projection vector itself, the projection of vector a on vector b will be nothing but the length of the projection vector, times the unit vector in the direction of B vector. So unit vector in the direction of B vector can be this much. Its length, its magnitude will be 1. And how do I calculate B cap? B cap is nothing but B vector upon its magnitude. So it is nothing but length of the projection matrix, projection vector, times B cap is nothing but the B vector upon the magnitude of B vector. This is what B cap is. This is how we define any unit vector, right? So this will be the projection. This will be the projection. Now we already know the length of the projection. It is the magnitude of A times cos theta. So if I just substitute it, I'll get magnitude of vector A times cos theta times magnitude, times cos theta upon magnitude of vector B times vector B times vector B. Okay, now cos theta is what? Again, we already know how to calculate the angle between two vectors, right? So there we can do it using their dot product. So the dot product of vector A and vector B is what? Magnitude of vector A times magnitude of vector B times cos theta. So from here we can say that cos theta will be nothing but their dot product upon their magnitudes, right? This is how we calculate the angle. So from here I can take the value of cos theta and I'll get magnitude of vector A times vector A dot vector B upon vector B magnitude times magnitude of vector A times magnitude of vector B times B vector. This entire thing is a scalar, and at the end we have B vector. Okay, we are multiplying it with B vector. So the magnitude of vector A and magnitude of vector A cancels out, and this is what we get. We get A vector dot B vector upon magnitude of A vector, magnitude of B vector square, magnitude of B vector square times B vector. This is the projection of vector A on vector B. This is the projection of vector A on vector B. Okay, we just proved it. This is the same formula we saw in the last slide, and this is what we just proved. Okay, so if you multiply this particular scalar to vector B, you will get the projection of vector A on vector B, and notice that the direction of this particular vector is same as the direction of vector B, obviously, because we are multiplying something to vector B. So this is how we can calculate the projection. Okay, so let's see an example. What is the projection of 2, 3 on 1, 0? So what do we want? This is x-axis, this is y-axis. Okay, vector A is 2, 3. So it will be, let's say this is 1, this is 2, this is 3. Here we have 1, 2, 3. So vector A is 2, 3. So x-axis is 2 and y-axis is 3. This is vector A. Okay, and we want to find the projection of this vector on 1, 0. What is 1, 0? 1, 0 is 1 units in x and 0 units in y. It is nothing but I cap. Vector B is nothing but I cap, right? A unit vector in x-axis. This is vector B. This is vector B, 1, 0. So we want to find the projection of this vector on this vector. It is very easy. So here vector B is smaller. So let's create the direction completely. This is the entire direction. We want to just compute the projection of A vector on x-axis, because B vector is x-axis only. Okay, the direction of B vector is x-axis only. So we want to compute the projection. If I put a torch here, and I want to find the projection, the image which vector A makes on x-axis, obviously we can see it directly. It should be this vector. This is the projection. This is the projection of vector A on vector B, and very easily we can see that it is nothing but 2, 0. Okay, so projection on x-axis and y-axis is very simple. If you want to project any vector on x-axis, you just take its x component times I cap, right? You will just get it. And if you want to project any vector on y-axis, you just take its y component. But let us try to get the same thing using the formula as well. If I try to get the same thing using the formula, what will we have? So the projection of vector A on vector B will be A vector dot B vector upon the magnitude of B vector square times B vector. What is the dot product of these two vectors? 2 into 1 plus 3 into 0. And what is the magnitude of b? It is 1 square plus 0 square. Then we will have square root and then again square. This is what we are doing, square root and then again square. So square root and square cancels, times b vector. Times b vector is 1 comma 0. I'm just writing the vector as it is here, right? Because we are essentially trying to multiply a scalar with a vector, I can just multiply the same scalar with both the values, right? Or if you want, you can write a matrix. I just wrote the components here. What is it? 2 plus 3 is 2 plus 0 is 0. 2 upon 1 times the vector 1 comma 0. So it is 2 times the vector 1 comma 0. So we'll get the vector 2 comma 0. This is the vector that we will get, 2 comma 0. So this is the projection 2 comma 0. That's what you found as well, right? So this is how we can calculate the projection using the formula. Now let's take a look at one more question. Find the projection of vector A 1 comma 2 comma 3 on the vector 4 comma 0 comma 0 comma 2. So I'll be unable to create a 3D space here. Let's try to directly use the formula and try to find it. So projection of vector A on vector B will be what? It will be A vector dot B vector upon the magnitude of B vector square times B vector. So A vector dot B vector is 4 into 1 plus 2 into 0 plus 3 into 2, and magnitude of B vector square will be 4 square plus 0 square plus 2 square, and then square root and square, so that will cancel, times B vector. B vector is 4 0 2. Okay, or you can write it 4 ik plus 0 jk plus 2 k cap as well, but I am just writing it in component notation. So 4 plus 0 plus 6 is 10 upon 16 plus 4 is 20 times 4 comma 0 comma 2. So it is half of this, 1 by 2 of this. So I'll get 2 comma 0 comma 1. This is the projection of vector A on vector B. Okay, and we will try to see in the software also, like the projection is like this or not. I'll try to create the equation and show it to you. Okay, let's look at another example. Here we have vector A as 3 comma 4 and vector B as 1 comma 2, and we want to find the length, we want to find the magnitude. Just look at the question carefully. We have to find the length of projection of vector A on vector B. So length of projection of vector A on vector B is what? It's just the magnitude of vector A times cos theta, right? And cos theta is nothing but A vector dot B vector upon magnitude of A vector times magnitude of B vector. So this and this will cancel and we'll just get the length. Length of the projection is A vector dot B vector upon the length of B vector. This is the length of projection of vector A on vector B. So here the cos theta, like the dot product will be 3 into 1 plus 4 into 2. And length of vector B will be square root of 1 square plus 2 square. So we'll get 3 plus 8 is 11, 11 upon root 5. 11 upon root 5. This is the length of projection of vector A on vector B. Okay, so this is the length. This is how you can find length. This is the formula as well. The length of the projection is this much. Cool. Now let's look at the concept of projection matrix. What is projection matrix? See, later in the course we will see transformation matrices in general. Projection matrix is also a type of transformation matrix. Let's not go into transformation matrix for now. Let's try to just look at projection matrix. So what is projection matrix? I told you in linear algebra we will be seeing again and again, we will be seeing vectors as matrices, right? And more specifically, generally we use a column matrix, and a vector represented in column matrix form is called a column vector. It is called a column vector, right? So what is a projection matrix? So let's say vector A is written in a column vector form. So this is how it is written: A1, A2, An. It is in n dimensional space, so it is an n cross 1 matrix, n cross 1 column matrix. So vector A is written in a column matrix notation. So what matrix do I multiply it with? So projection matrix is nothing but a matrix. So I want to multiply matrix A with a matrix P such that I get the projection vector. So projection matrix is defined as a matrix which, when multiplied by a vector gives you the projection of that particular vector on another vector. So this particular projection matrix will be specific to vector B. It will be specific to vector B. So why? Because we want to find projection on vector B. So what will happen if you want to find projection now? You just take this projection matrix and you multiply it with any vector. You multiply it with any vector and you will always get the projection. You will always get the projection of vector A on vector B. And this will be the projection matrix of vector B. I want to create one such matrix which when multiplied with any vector gives me the projection. Essentially we are transforming vector A, right? This particular matrix, if I multiply it with any vector, I'll get that particular vector's projection on vector B. It is a magical matrix, right? It is a magical matrix. And now notice that whenever you are trying to find a projection on vector B also must be of the same dimension n cross 1. See also, when you are trying to find projection of a vector on another vector, both the vectors should be in the same dimensional space. If their dimensions are different, you cannot find the projection. So vector A and vector B must be of the same dimension. If vector A is n cross 1, which means n dimensional space, B also is in n dimensional space. And the projection will also be in an n dimensional space. So projection vector is also an n cross 1 matrix. So I want to get n cross 1 matrix when I multiply it with P. So P must be an n cross n matrix. P must be an n cross n matrix. Why? Because for confirmability, these two values must be same. The number of columns in B in the projection matrix must be equal to the number of rows in A. Then only I can do this multiplication, right? So P must, like these two must be equal, and the final result that I want must be an n cross 1 vector, because the projection is also in n dimensional space, and hence this value also must be equal to n. So projection matrix will be an n cross n matrix. So if B vector is an n cross 1 vector, then its projection matrix PB will be an n cross n matrix such that whenever you multiply PB with any vector A, you will get the projection of vector A on vector B. This is what you want to find. Okay? And it's not very difficult. This is the projection matrix. This is a matrix. This is an n cross n matrix. This is an n cross n matrix. How? We will see. So the hypothesis is the projection matrix of any vector B will be BB transpose upon B transpose B. Very beautiful formula, right? BB transpose upon B transpose B. But how? So let's try to derive that. So the hypothesis is projection matrix for n dimensional n-dimensional vector B. Let's say it is in n cross 1. It is an n cross 1, which means it is represented as a column vector. Is PB, it will be of dimension n cross n, and it is given by BB transpose upon B transpose B, and it will have a property that whenever you multiply this PB matrix with any vector A, you will just get the projection of vector A on vector B. This is what will happen. So based on this property, can we find this matrix? See, in this matrix there is no involvement of A, there should not be. It is just dependent on vector B. So this is what we want, okay, at the end of the day. And this is what we want to prove. Okay, this will be the vector. Now firstly let's try to see the dimension. So the dimension of this BB transpose upon B transpose B will be what? B is a column vector here. It is an n cross 1 vector. So B transpose B is what? It is 1 cross n times n cross 1. So this denominator will be a 1 cross 1 matrix. It is a scalar. Denominator is a scalar, and we already know for any column matrix B transpose B is nothing but the magnitude square. It is nothing but the dot product. I told you, right? If you want to compute the dot product of any two vectors, you can just do A transpose B if they are both represented as column vectors. In the last lecture we have seen this. When we were discussing dot products, we have seen if we have two column vectors in the same dimensional space, if I just compute A transpose B, I'll get the dot product of these two. So here B transpose B, or the denominator, is nothing but the dot product of B with itself. The dot product of B with itself. Okay. Okay, so this is a scalar, and the numerator is BB transpose. BB transpose is what? it is an B is an n cross 1 matrix, B transpose is a 1 cross n matrix, and their multiplication will be an n cross n matrix. So overall it is an n cross n matrix upon a scalar. So it will be an n cross n matrix at the end of the day, and that's what we wanted. We know that projection matrix should be an n cross n matrix. Okay, so it will be n cross n matrix. Okay, cool. I'll write it here: 1 cross n cross 1. So it will be n cross n. Okay. So how do we prove it? So we already know this particular property. Okay, so let's start from here. So we want projection matrix of vector B such that this happens. Now projection of vector A on vector B is what? We have already computed it. We already know it is A vector dot B vector upon a magnitude of vector B square times vector B, right? Now I just want to prove that PB is that value. I just want to prove that PB is that value. So I just want to prove that this will be equal to PB is what? BB transpose upon B transpose B times A vector. Now notice here that here it is a scalar. This is a scalar. We already know this is an n cross 1 vector, and A vector is also an n cross 1 vector, and this is an n cross n vector. So if I multiply n cross n with an n cross 1, I'll get an n cross 1 vector at the end. So dimensions match. This is what I want to prove. So we want to prove that this value is equal to this value. If we just prove this, we actually have proven that PB is that. The projection matrix is that particular matrix. Okay. So how are these two quantities equal? So firstly, B transpose B. If I see the denominator is actually equal, because B transpose B is what? B transpose B is B dot B, right? The dot product of B with itself. And the dot product of B with itself will be what? The magnitude of vector B times the magnitude of vector B times cos theta. Now the angle of B vector with itself will be what? 0 degrees. The angle of B vector with itself will be what? It will be 0 degrees, and hence B vector dot B vector will be magnitude of B into cos 0. Cos 0 is 1. So it will be just magnitude of B vector square. So the denominator, which is B transpose B, is nothing but magnitude of B vector square. So denominator are matching. Denominator is matching, right? This is nothing but magnitude of B vector square. I just want to, and they are both scalar. This is also a scalar, this denominator, and this is also a scalar. So that is fine, right? What do we want to do next? We want to prove that the numerator is also same. Here the numerator is A vector dot B vector times B vector. And here the numerator is B vector times B transpose B into B transpose times A vector, okay, times A. So let's not use vectors, let's use matrices now. So we will just prove that A into B vector will be same as B into B transpose into A vector. Now here A vector is an n cross 1 column vector, B vector is also an n cross 1 vector, okay. Sorry, this is a dot product. This is not matrix. This is not matrix multiplication. This is dot product. So here I have to write vector. But here I can write it n cross 1. This is a matrix. And here B is an n cross 1 matrix. B transpose is a 1 cross n matrix. And A is an n cross 1 matrix. So this is what we want to prove. So we can write A vector dot B vector as in the matrix notation also, right? Then only we'll be able to prove it. So A vector dot B vector we know is A transpose into B. In matrix notation, that's how we calculate the dot product. The dot product of A vector and B vector is A transpose into B. Now A transpose is a 1 cross n matrix, B is an n cross 1 matrix, so their dot product will be a 1 cross 1 scalar. So this is what we want to prove. And this happens only because of dot product property, okay, we will see why. So now what will happen? Matrix multiplication is commutative. Right, matrix multiplication is commutative. A, B, C. If you are multiplying two matrices, I can do it this way. This will be equal to A times BC in matrix. Right? Matrix multiplication is commutative. So I can write this RHS is as B times B transpose A. B transpose A. Right? I can write it this way because matrix multiplication is commutative. Now B transpose A is nothing but the dot product of A vector and B vector. Right, B transpose A is also equal to the dot product of A vector and B vector. This is also equal to A vector dot B vector because dot product is also commutative. Matrix multiplication is associative, and that's why this happens. and dot product is commutative. A vector dot B vector is equal to B vector dot A vector. We have already proved it. And you can write it as A transpose B or B transpose A. You will get the same answer in matrix notation, right? In the last lecture we have seen this property. And hence B transpose A is also equal to A vector dot B vector, and it is a scalar. And scalar you multiply on the right side or left side, it doesn't matter. I can write this one also as A vector dot B vector times B vector, which is nothing but LHS, right? Which is nothing but LHS. And hence these two vectors are essentially same. So and hence this particular way of representing can be represented using this way as well, right? Here we are doing some scalar times B vector. Here we are doing a matrix, n cross n matrix times A vector, and essentially we are getting the same answer. And we have proved it. Okay, this is proved. And hence these two are essentially same, and hence we can say that this entire thing is the projection matrix for vector B. Okay, if you don't remember the proof, it's okay. But if you know the proof, you don't forget the formulas in exam, right? So try to see and understand the proofs as well. Beautiful. So this is the projection matrix. For any vector B, now we can compute a projection matrix, which when multiplied with any vector will give you the projection of that vector on vector B. Okay. Cool. So to prove the same hypothesis, let's try to solve the examples. Before examples, we will see some properties of projection matrices. Every projection matrix is idempotent, very important property, and this property holds true only for projection matrices. Later we will see more transformation matrices. This particular transformation matrix, n cross n matrix, is projection because it is giving you projection. Later we will see other type of transformation as well. But the only transformation matrix which is idempotent is the projection matrix. It is idempotent. P square will be equal to P. It is beautiful. Why? Because think about it. What is the projection matrix doing? When you multiply the projection matrix with any vector, it gives you the projection of that vector on vector B. If you again compute the projection of that vector, so what will happen? So let us say this is a vector A and this is a vector B, and this is the projection. This is the projection of A vector on B vector. So let's call it P vector. P vector is the projection of A vector on B vector. Now if you again compute, so how did we get P? P vector was the projection, which means projection matrix times A vector, right? If I again multiply the projection matrix with P vector, what are we trying to do? We are trying to calculate the projection of P vector on vector B. We are trying to calculate the projection of P vector on vector B. But the projection of P vector on vector B will be the same vector again. It will be the same vector again, right? And hence PB times PB times A vector is again P vector, and hence PB times PB is nothing but the PB vector, right? And hence every projection matrix will always be idempotent because of this property. Because if you take the projection of a projection, you will get the same projection. You can only take projection once. After that, you will keep getting the same vector, and hence for any projection matrix, its square will be the same matrix. Okay, and yep. You can, and if you want a detailed proof, you can take the square of this matrix and you can prove that it will be equal to the same matrix. I will give you that as homework. Try to take the square of this and prove that it will be equal to the same matrix. Okay, and also it will be symmetric. Every projection matrix will be symmetric. It will be idempotent and symmetric, which means P transpose will be equal to P. Now this thing we can prove. So what is P? P, the projection matrix, is an n cross n matrix, which is BB transpose upon B transpose B. If I take the transpose of it, it will be the transpose of this entire matrix. So the denominator is a scalar. So for a scalar, even if you take the transpose, you will get the same scalar back, right? For a 1 cross 1 matrix, if you take the transpose, you will get the same matrix. So denominator we don't need. But for numerator, the numerator transpose will be what? BB transpose transpose. The transpose of the numerator is, we know that for any two matrices, AB transpose is equal to B transpose A transpose, right? Transpose when opened on a bracket opens backwards. We know this thing. So it will be B transpose transpose times B transpose. So it will be B times B transpose again. So the transpose of numerator is the same matrix and transpose of denominator is also the same matrix, and hence the transpose of projection matrix itself will always be the same projection matrix, and hence any projection matrix will be symmetric and every projection matrix will be idempotent in nature. P square will be equal to P. Cool. Now let us look at examples. So this is the first example, again the same examples that we solved before, but now we will try to solve them using projection matrix. We already have calculated this projection of a vector A on vector B. But firstly, let's try to find the projection matrix for vector B now here. Which is, vector B is here is nothing but I cap, right? Unit vector in x direction. So what is the projection matrix for vector B here? It will be BB transpose upon B transpose B, where B is a column matrix. B is a column matrix 1 0 like this. Okay, always represent vectors in column matrix notation while using these formulas. For row matrices they will change. Cool. So what is B transpose B? B transpose B is nothing but okay, let's calculate 1 0 times 1 0. So it will be 1 plus 0, which is 1. Okay, it is the magnitude of B square. So it is 1. And what is BB transpose? So you will get 1 upon 1. So denominator is 1 only. So you will get 1 by 1 times BB transpose. B is 1 0 and B transpose is 1 0. BB transpose is an n cross n matrix. So this is a 2 cross 1 matrix and this is a 1 cross 2 matrix. So when you multiply them, you will get a 2 cross 2 matrix and you will multiply it with 1. So you will get the same matrix back. So let's compute it. 1 into 1 is 1. 1 into 0 is 0. 0 into 1 is 0 and then 0 into 0 is 0. This is the projection matrix for x-axis. You can multiply any vector with this matrix and you will get the projection of it on x-axis. Okay, this is the projection matrix of any vector on 1, 0. Now if you want to find the projection, you just multiply it with a vector to get the projection. So projection of vector A on vector B will be projection matrix times A, which is 1 0 0 0 times 2 3, and we will just have the x component. So we will have 2 plus 0, which is 2, and then 0 plus 0 is 0. 2, 0. This is the projection. We already calculated it, it matches. Okay, so this is the projection matrix. Now if we do it on the same on the 3 cross 3 example, which is this one, here we have A vector is 1 2 3 and B vector is 4 0 2, and hence the projection matrix of matrix B will be BB transpose upon B transpose B. Now B transpose B will be 4 0 2 times 4 0 2, which is 16 plus 4, which is 20. So it will be 1 by 20 times BB transpose. B is 4 0 2 and B transpose is 4 0 2. So it will be a 3 cross 3 matrix. So it will be 1 by 20 times a 3 cross 3 matrix. 4 4s are 16. Okay, so this is a 3 cross 1 matrix and this is a 1 cross 3 matrix. So at the end we will get a 3 cross 3 matrix, which is correct. So 4 4s are 16 and then 4 zeros are 0, 4 2s are 8, then 0 0 0 and then 2 4s are 8, then 0 and then 2 2s are 4. This is the projection matrix. So if I divide every value by 20, what we will get? 16 by 20 is 4 by 5, 0.8, then 0. Then 8 by 20 is 2 by 5, which is 0.4. Then we will have 0 0 0. Then 8 by 20 is again 0.4. Then 0 and then 4 by 20 is 1 by 5, which is 0.2. So this is the projection matrix for this vector. You multiply any vector with this matrix, you will get the projection. So now if you want to find the projection of vector A, it will be just you multiply this projection matrix 0.8, 0, 0.4, 0 0 0, 0.4, 0, 0.2 times the vector A. Vector A when represented in column vector will be 1 2 3. So you will get a 3 cross 1 vector again. 0.8 plus 0 plus 1.2. 0.8 plus 1.2 is 2. Then we will have 0 plus 0 plus 0 is 0. Then we will have 0.4 plus 0 plus 0.6, which is 1. So this is the vector 2 0 1. And we got the same vector when we solved it before as well. Okay, so this is the projection of vector A on vector B using projection matrices. Okay, this is also how we can do it. Cool. So this is all about projection of a vector on another vector and how do we use projection matrices. Later when we see spaces and subspaces, we will see more advanced concepts like projection of a vector on a space, projection of a space on another space. It will be crazy. But yeah, that's all for this lecture. For a vector, now you can compute the projection and the matrix. I hope everything makes sense. And we will solve more examples in the next lecture. Thanks for watching this one. Let's meet in the next one. Bye-bye.